Alright, grade 12 chemistry. This is a video on calorimetry problems. Today our learning goals are to learn about specific heat capacity, and then the big goal is to apply that concept of specific heat capacity to predict how much temperature change we're going to see in a chemical reaction. So here's our learning goals. We're going to start talking about calories and calorimetry because it's an important concept to explain heat capacity. Then specific heat capacity. So this concept, you might remember that from physics if you've taken physics. We're going to do an example of it, just a straight up heat capacity problem, and then we're going to do an example of using it in a chemical reaction to predict a temperature change. So that's our goal today. Probably most of it's going to be spent on the practice problems. Okay, jumping in. What's a calorie anyway? So calorie is actually an old unit. It's an old unit of energy, an old measure of energy based on how much energy it takes to heat 1 gram of water by 1 degree Celsius. So it's the amount of energy to heat 1 gram of water by 1 degree Celsius. If we convert it to SI, which is joules, it's 4.184 joules. So 4.184 joules, that's 1 calorie. So it takes 4.184 joules of energy to heat 1 gram of water by 1 degree Celsius. A kilocalorie, kilo like kilometer is 1,000 meters, it's 1,000 calories. Or sometimes written big C calorie. This is 4,184 joules because it's 1,000 times bigger than this number. Or 4.184 kilojoules. So this is a measure of energy. So with a kilocalorie, you could heat 1,000 grams of water by 1 degree Celsius. Or you could heat 500 grams of water by 2 degrees Celsius, or 250 grams of water by 4 degrees Celsius, blah, 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 blah. Any kind of combination that multiplies to 1,000. It's a measure of energy. Here's an example of a Coca-Cola label from Great Britain where it actually has the calories and the kilojoules on one label, and you can see it's about 4 times more, right? Approximately 4 times, because a calorie is 4 joules. A kilocalorie is about 4 kilojoules. Yeah, 4.2, right? So yeah, that's calories. That's what calories are. This comes from an old unit of measurement back when they would measure things with physical properties, because that's the best way they could do it. They could measure how much water you had. You could weigh how much water you had, and you could measure how much the degrees Celsius changed, how much the temperature changed by. And so they worked out a unit of energy based on this. It's actually Joule himself that worked it out. He called it the thermal equivalent of work. And so it's kind of funny that he's the one that came up with this concept of calorie, and then we named the unit that supplanted it after him. It's kind of an interesting historical fact. All right, what's a calorimeter? How do they figure out food's calorie content, right? How do they get this? Well, actually nowadays they just take how much sugar and how much fat and how much whatever, and they have big tables of this, and they just put it together and they figure out how many calories are in the thing. But back in the day, and they still do this in, as far as I know, they still do this in certain chemistry labs when you do thermochemistry. You take the food and you put it into this thing called a bomb calorimeter. In there, there's oxygen, just oxygen gas, and you literally burn the food, because that's what humans do, right? We take food and we combine it with oxygen to break it down and extract the chemical energy. So they literally burn the food in this little bomb here with oxygen gas, and then that's surrounded by water, a known quantity of water, right? Maybe, I don't know, 500 milliliters of water, 500 grams of water, or a kilogram of water to make it easy. And as the food burns and the oxygen, as it reacts, the water will heat up, and based on how much the thermometer changes, you figure out how much energy. That energy comes in the form of calories, right? Because you're heating up a certain amount of water by a certain degree Celsius. So you can figure it out in calories. And so it's called a calorimeter. It's a device that uses the temperature change of water to figure out how much energy got transferred in a chemical reaction. Now, it doesn't have to be a food reaction. It doesn't have to be food and oxygen. You can do this with a chemical reaction, any other chemical reaction. You could, I don't know, dissolve some salt in the water and see if the water goes up or down in temperature. You can do the like vinegar baking soda reaction and see if the temperature goes up or down. You know, things like that. Yeah, so that's a calorimeter. Figure out how much energy is released as the temperature rises. So that's how they figured out the stuff at the start. And now they just have tables. They know that, you know, glucose has this many calories per gram and fat has this many calories per gram. They just put it all together and they figure out how many calories are in the food. Yeah, so that's calorimetry. That's what calorimetry is. Next up, we're going to talk about specific heat capacity. So we're going to pause for a sec. Heat capacity. So water is very good at absorbing heat. You know this if you've ever, you know, been in a bathtub or jumped in a lake when it's like really, like right now it's May and it's like 22 degrees outside. But if I went and jumped in a lake or a river, that lake would be really cold because there's a lot of inertia, right? There's kind of thermal inertia to, it takes a lot of energy to heat up the water. A lot of energy is released when the water cools down and the water heats up the land. This is why, you know, the coasts have less temperature difference than the interior in geography. Things like that. Water is very, very good at holding on to heat, and it takes a long time to change water's temperature. This is something called specific heat capacity. Specific heat capacity. So the word is very, very well chosen. It is the capacity of a substance to absorb or release heat. It's specific to each substance. And heat, being used here, heat, is the amount of thermal energy transferred, right? The amount of thermal energy transferred. It has a symbol. The symbol is C. C. It's actually small c. So small c for capacity. And it's measured as the number of joules it takes, right? The energy in joules that it takes to raise the temperature of 1 gram of the substance by 1 Kelvin on the Kelvin scale. But Kelvin is the same scale as Celsius. So 1 Kelvin, one jump of 1 Kelvin is the same as one jump of 1 degree Celsius. So you could say it 1 gram by 1 degree Celsius just as easily as 1 gram by... You also sometimes see kilojoules per kilogram, but it's 1,000 per 1,000, so it cancels out. It actually get the same number, but it's kilojoules per kilogram instead of joules per gram. And on occasion, you'll see joules per kilogram. Yeah. And this is how it works, right? We know that it takes 4.184 joules to heat 1 gram of water by 1 degree Celsius. This is a known quantity in chemistry. That means if I had 3 grams of water, right? If I had 3 grams of water, I wanted to heat it by 1 degree Celsius, it's 3 times more water, so it'll take 3 times more energy. So it'll take 12 joules, 12.5 joules, right? Or if I had this just 1 gram, but I want to heat it by 3 degrees Celsius, I'm heating it up by 3 times more, right? I need to put in 3 times more energy because 1 degree, 2 degree, 3 degrees. So it's going to be 3 times more. So that's also going to be 3 times 4.184, 12.552. But if I had 3 grams of water and 3 degrees Celsius, now I've got 3 times more water. So that's 3 times more energy per degree Celsius and 3 times more temperature change. So 3 degrees Celsius, that's going to be 3 times 3. It's going to be 9 times more energy than the 1 gram by 1 degree Celsius. So that's how this kind of stuff works. So it'd be 4.184 times 9. So 37.656. And so the formula is very, very simple here. I'm going to move my thing. Formula is Q equals mCt. Q equals mCt. And again, I believe that's a small c. So Q, heat, right? Heat in, heat out. You can have negative Q if it's losing temperature, right? Mass is always positive. C is always positive. Temperature can be, change in temperature can be positive or negative. So you can have a negative heat if the substance is losing energy, if it's cooling down. So that's Q's negative heat. Yeah, M is mass, C is specific heat capacity. So here's a question, right? How much energy would it take to increase the temperature of 250 grams of water from 21 degrees Celsius, so room temperature, to 100 degrees Celsius, which would be, boiling. So this would be like boiling a cup of water. How much energy would it take? Well, we have to kind of put in some knowns, right? Here's our formula down here. Q equals opposite T. Q is what we want. We want Q. How much energy? Do we have M? Of course we do. We have M is 250 grams. C, the heat capacity. We have to see what is our substance. It's water, right? Liquid water. Liquid water. And we know that that's 4.184 joules per gram degree Celsius. I'm just going to do the fake kind of degree Celsius because I don't have the degree symbol on hand. There we go. Joules per gram degree Celsius. And our change in temperature, right? Change in temperature, delta T, right? Change in temperature is how much? Well, we're starting at 21 degrees Celsius and we want to go to 100 degrees Celsius. So it's 100 minus 21, right? It's plus 79 degrees Celsius. Plus 79 degrees Celsius. That's an important step here because if you just choose 21 or 100, that's not suggesting a change in energy. It's just, you're trying to do some kind of absolute energy thing, which is not what we're interested in. We're interested in a change in energy, right? So that delta is very important, figuring out that you're increasing the temperature by 79 degrees Celsius. And then the actual calculation is, you just throw it through your calculator, is 250 grams, right? 250 grams, that's the mass, times 4.184 joules per gram degree Celsius, times plus 79 degrees Celsius, right? 79 degrees Celsius. Just really quick, a good thing to do here is to check that the units are going to cancel out appropriately. So I'm actually going to jump over to to this guy here, right? We've got, here's our formula. Q is equal to 250 grams times 4.184 joules per gram degree Celsius times plus 79 degrees Celsius, right? Plus 79 degrees Celsius. And we just want to check to make sure that the units are going to cancel out because we want Q. Q should be in joules. So the grams is on top here. It's going to cancel the grams down here. Grams are canceled. That's good. The degrees Celsius down here is going to cancel the degrees Celsius here, and we're left with just joules. Joules per 1, right? They reduce to 1. And then we throw that through a calculator and we figure out what we get. So get the calculator. 250 times 250 times 4.184 times 79, 82,634 joules. 634 joules, or 82.634 kilojoules. There we go. Right, and then we can put that into our equation. So we'll put that in here. 82,604 joules of energy plus. It's a plus. It's a positive. So it's gaining energy. The water is gaining energy, which means the surroundings are going to lose energy. It's a lot of energy. 82,000 joules is a lot. Water has this very high heat capacity. If you've ever had to, boil water to make pasta or whatever, you know that it takes a while. So, yeah, that's a basic heat capacity problem. We're going to go to a more complicated one in a second, but here's some various heat capacities just to show you that water is really cool. Water has this very high heat capacity in terms of joules per gram degree Celsius. It's actually twice as high as ice or steam, which is interesting because that's liquid water, solid water, and gas phase water. Different phases actually have different heat capacities. This is mostly down to hydrogen bonding between the water molecules. Metals have a relatively low heat capacity most of the time. You see that like aluminum and chromium and copper and lead, quite low. This is sometimes a good thing. So copper, for example, is used in a lot of heat transfer applications as heat pipes because it's very easy to heat it up and it'll move the heat, conduct the heat away very easily. Chromium 0.4, lead 0.127 is a very low heat capacity. Silver, tin, titanium, and then a few other ones. Joules per gram Kelvin. Air has a heat capacity, which is kind of cool. It's how much energy it takes to heat up the air. It's actually a lot lower than water's. It's a quarter of water's. Water's is 4, air's is 1. And also air is less dense, right? There's a lot less grams of air per volume. And so this is why the air can heat up very quickly, but water takes a long time. This is why it can be 22 degrees Celsius outside right now, which is being heated by the sun. Meanwhile, the water is still very cold. And it would be hard for me to jump into the water. An interesting thing here is look at helium and hydrogen, 5 and 14.3. 5 and 14.3. Very, very high heat capacities, but again, they're very low density gases. So overall, it doesn't come out anything. Plastics often have a fairly high heat capacity. So polyethylene, quite a decent heat capacity. Kind of cool. And this one here, the heat capacity is given in joules per kilogram times Kelvin. So joules per kilogram Kelvin. So that means that it's 1,000 grams. That's how many joules it takes to heat 1,000 grams instead of 1 gram. So this is for 1 gram. This is for 1,000 grams. And because it's 1,000 times the amount of stuff we're trying to heat, the numbers are 1,000 times bigger. The amount of joules is 1,000 times bigger. So you see here for aluminum here, it's 897 joules per kilogram, but over here it's 0.897 joules per gram. It's exactly what we expect because it's 1,000 times more material. Let's do a problem. Let's do a practice heat capacity problem, and I'm going to pause. All right, practice problem for heat capacity. The big idea here is that the heat lost by this block is going to be gained by the water. So we have this 24.2 gram block. It's heated to 100 degrees Celsius and then put into 120 grams of water. The water starts at 32.8 degrees Celsius. And the final temperature of both the water and the metal together becomes 34.5. So the block went from 100 to 34.5, so like 70 degrees Celsius. The water went from 32.8 to 34.5. And the first question is, why did the metal block reduce by almost 70 degrees? The water only increased by about 2 degrees. And to do that, that's a way to get you guys to think about what's actually happening here. We're going to jump over here, and I'm going to erase this. And we are going to kind of diagram what's going on. So here's our, the calorimeter is just going to be a cup of water. Here's our water. Right, we'll put the water in there. And we'll stick the metal block in as a little metal block like that, right? It's not very big. It's 24 gram block. So this is 24.2 grams, right? And the water was 120 grams of water. The water has a heat capacity of 4.184 joules per gram degrees Celsius. We know that. The metal block, we don't know its heat capacity. But we know that it started at 100 degrees Celsius. So the metal block started at 100 degrees Celsius, and the water started at 32.8 degrees Celsius. 32.8 degrees Celsius. The metal block went to 34.5 degrees Celsius. The water went to 34.5 degrees Celsius. So, the question becomes, why did this lose so much temperature, but this only gained a little bit of temperature? Well, there's a couple of reasons. Number one, look at the mass. There's a lot more mass of water. There's like 5 times more water than this one, right? 5 times more water than metal. Number 2, water has a high heat capacity compared to most metals. If you look at the list, right? If you look at the list here, water is 4, and metals are like 0.4, 0.2, 0.3, stuff like that. So there's a higher heat capacity and more water, 5 times more water, and probably something like 5 times more heat capacity. So what happened here was heat, right? Heat, thermal energy, went out of the block and into the water. And this is where the keep in mind comes in. Keep in mind up here, right? Up here. Q1 is negative Q2. This means that the heat that was gained by the water must have come from the block and only from the block, which tells us that Q block, right? Q block, or negative Q block because it lost, is the Q of the water. Q of the water. Right. So next question here is calculate the amount of thermal energy transferred from the block to the water. Calculate the amount of energy transferred. Well, to do that, we need our equation, right? Q equals m times c times delta t. Which one can we know? Well, we don't know the capacity of the block. We don't know what heat capacity the block had. But we do know the heat capacity of water because it's given. And we know it's 120 grams, and we can figure out the delta T here. The delta T, the change in temperature, it started at 32.8, it went to 34.5. So it must have gone up by 1.7 degrees Celsius, plus 1.7 degrees Celsius, because it increased by 1.7 degrees Celsius. So then we can just put that in the equation, right? The Q of the water is going to be the mass of the water, which is 120 grams here, 120 grams, times the capacity of water, 4.184 joules per gram degrees Celsius, times the delta T, the change in temperature, plus 1.7, right, plus 1.7 degrees Celsius. Check that our units cancel out. Grams cancels grams, degrees Celsius cancels degrees Celsius. We were left with joules, so that's good. And we put it through a calculator, and we get an answer. 120 times 4.184 times 1.7. I get 853.5 joules. Well, plus 853.5 joules plus 853.5 joules. 853.5 joules. So that's how much energy we know that the water gained just by how much the temperature of the water increased. Now, based on the law of thermodynamics, right? Based on the law of thermodynamics, that amount of energy must have come from the metal. So that tells us that the Q of the block must have been the negative version of this, must have been negative whatever the water gained, because we assume this is a closed system. So it's minus 853.5 joules. That's the Q of the block. Q of the block. Which lets us solve the last part of this question. The last part of this question is determine the specific heat capacity. Determine the specific heat capacity of the metal. Right? So going back to here, and I'll move this down a little bit. We know how much energy the metal lost. We know, or we can figure out, how much temperature the metal lost. It went from 100 to 34.5. So if you take 100 minus 34.5, you get delta T here is minus 65.5 degrees Celsius. So we know delta T. We know the mass, 24.2 grams. C is the only thing we're missing in our equation. Remember that our equation is Q equals M times C times delta T. Right? We have Q, It's the minus 853.5. We got that from the water side of things. It's the negative version of that. We have M, that was given to us in the question, 24.2, and we worked out delta T from the starting and finishing temperature. We have that. So we just need to solve for C, and we can. We rearrange, so C becomes Q divided by M times delta T. And then we can plug in our formula and solve. We can just plug in our numbers. So Q is minus 853.5 joules. Right, minus 853.5 joules. M is 24.2 grams. And delta T is minus 65.5 degrees Celsius, because it's the change that we're interested in, divided by, that. Now we have to be careful when we're putting this into our calculator to make sure that both things end up on the bottom. So usually I suggest just using brackets. So I'm going to go minus 853. Can you see that okay? That's hard to see, eh? Minus 853.5 divided by, I'm going to open a bracket, 24.2 times 65, minus 65.5, minus 65.5. And go close that bracket, and then I get my answer, 0.538. 0.538. 0.538. And we need a unit on this thing. We need to figure out what unit our heat capacity is in. Well, look, it's joules per gram degree Celsius. It's right there in our problem. That's why we write units into our calculations. Joules per gram degree Celsius, which is what we expect heat capacity to be in. But it's always good to check, right? So we got 0.538 joules per gram degree Celsius. Yeah. And so you can figure out what the heat capacity of this metal was by just measuring how heavy it is, how much water you have, and the temperature difference, the temperature change. It's a way to actually figure out what metal you have. So let's do that. Let's figure out what metal we had. It was 0.54. If we go back here, 0.54, 0.54, yeah, those are kind of low, those are kind of low. Yeah, kind of low, kind of low. Titanium's a good fit, 0.52, could be titanium. Nothing else really comes close to 0.54. Maybe diamond, but not really a metal. I think it would be obvious if it was diamond. So yeah, we could probably say it's titanium, 0.52, and this is 0.54. That gives us 0.54. So that's a basic heat capacity problem. We're going to go to one that involves a little bit of chemistry next. This is our last practice problem. This one is using a chemical reaction. And here's some hints for these. The delta H value is always 1 mole of the reaction as written, or 1 mole of whatever reactant is highlighted. The other thing is that most reactions happen in water, and typically whatever we're dissolving is pretty dilute, so that we can just kind of keep the 4.184. This changes with like really high concentrations of like really salty water or anything like that. It'll change the heat capacity. But we're going to assume that we keep 4.184 for simplicity's sake. So here's the problem we're going to do. Right? The problem that we're going to solve is we have 500 milliliters of 1 molar HCl, meaning 1 mole per liter, and it's mixed with 500 milliliters of 1 molar NaOH, sodium hydroxide. We're given the heat of neutralization. It's 56.5 kilojoules per mole of HCl or NaOH. So let's go over to our whiteboard and write this out. Here's our reaction. HCl plus NaOH becomes H2O plus NaCl. And the delta H value of this reaction is minus 56.5 kilojoules. Kilojoules as written for 1 mole of each of these, right? So the kind of hidden thing here is when we write minus 56.5 kilojoules is that this is 1 mole of this, 1 mole of this, 1 mole of this, and 1 mole of this, right? 1 mole of each of these. But do we have 1 mole of it? Let's look at our question. We have 500 mils of 1 molar HCl and 500 mils of 1 molar NaOH. So going back to our grade 11 chemistry with our units, we have 500 milliliters, right? 500 milliliters, and it's 1 mole per liter of 1 mole per liter. And here we have 500 milliliters of 1 mole per liter as well. I was nice to you guys and I gave you equal amounts. 500 milliliters. So how many moles do I have? Well, eagle-eyed viewers might notice that 500 milliliters is the same thing as saying 0.5 liters. 0.5 liters, half a liter. And if each liter has 1 mole, well, 0.5 liters must have 0.5 moles, right? 0.5 moles of HCl and NaOH. So we are not going to release 56.5 kilojoules because we only have half a mole of each of these, half a mole, not the 1 mole that the minus 56.5 assumes. We only have half of that amount. If we have half of that amount, we must release half that much energy. Therefore, the Q, right, the Q of these chemicals is going to be the delta H over N. N being the number of moles of reaction we can do, or not over N, sorry, times N, delta H times N, delta H times N, times the number of moles of the reaction. So that's minus 56.5 kilojoules times 0.5 moles, right, kilojoules per mole, 0.5 mole. If we want to take away the, right, moles, they'll cancel out, you'll just get kilojoules. So whatever half of 56.5 is, which would be what, 28.25 kilojoules of energy? 28.25 kilojoules of energy. We are releasing 28.25 kilojoules of energy with our known amounts. That's how much energy we're going to release here. So we have that. And let's do a little diagram of what's actually going to happen here. Because the question is, what will be the temperature, right? If we look at the question is, what will be the temperature of the mixed solution after the reaction is complete, assuming we start at 25 degrees Celsius. So let's draw ourselves a little diagram. We have this. We mix some acid and some base together, right? The acid was 500 milliliters, and the base was also 500 milliliters, right? So together, we have 1 liter of water, of liquid water, 1 liter of water, which is 1,000 grams. 1 liter is 1,000 grams, 1,000 grams. Or we can keep it as 1 kilogram. That'll actually make things easier in a second. So 1 kilogram of water. That's just a known quantity, that 1 gram of water is approximately 1 milliliter, or 1 kilogram of water is approximately 1 liter. Specifically, that's true at 25 degrees Celsius. So this gives us kind of everything we need. We know that Q is, this was negative, right? Negative 28.25, but when they lose energy, the water must gain energy. So the water is going to gain plus 28.25 kilojoules of energy. The mass is 1 kilogram. The heat capacity, well, it's water. It's water. It's 4.184 joules per gram, or we can write 4.184 kilojoules per kilogram. 4.184 kilojoules per kilogram. The only thing we don't know here is delta T. What is delta T? Looking at our equation, Q equals M times C times delta T. We know Q because that came from the actual reaction. We know M, it's 1 kilogram. We know C, 4.184 because it's water. And delta T is our thing we don't know. We rearrange delta T is Q over MC. And then we just plug in the numbers, right? 28.25 kilojoules over 1 kilogram times 4.184 kilojoules per kilogram per degree Celsius. Kilojoules per kilogram degree Celsius. I forgot to put that on this side, kilogram degree Celsius. Let's check our units. The kilojoules will cancel kilojoules. The kilograms will cancel kilograms. We're left with degrees Celsius. It's divided by degrees Celsius, so it's going to come back up to the top. So we will get an answer in degrees Celsius. So therefore, delta T, if I put in the numbers, right? If I put in the numbers, 28.25 divided by, remember our brackets, 1 times 4.184, 6.75 degrees Celsius, plus 6.75 degrees Celsius. So that's the change in temperature that we're going to get, 6.75 degrees Celsius. This is going to go up by 6.75 degrees Celsius. When we look back here, we start at 25 degrees Celsius, so to figure it out, 25 degrees Celsius plus the 6.75 degrees Celsius that we just figured out, all right, is going to be, 31.75 degrees Celsius. All right, 31.75 degrees Celsius. All right, so that's how we figured it out. It's a big multi-step problem. I would lead you through this kind of like I did with the previous question. Next question, B, is does this change if we double the volumes? We still have the 1 molar HCl and the 1 molar NaOH, but we double the volume. Well, let's think about that. If we double the volumes, we have twice as much chemical, which means we'll release twice as much energy. But we also have twice as much water to heat up. We got double the energy and double the water, which is what's going to absorb the energy. That's going to cancel out. So no. 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 We have twice the chemicals, but also twice the water to absorb the heat, right? Twice the chemicals and twice the water that absorbs the heat. So they cancel each other out. Does this change if we double the concentrations, right? If we have twice the concentration, yes. Right? If we double the concentrations, we now have twice the chemicals in the same amount of water. Right? Twice the amount of chemicals in the same amount of water. So temperature change would double. Temperature change would double. Right? It would be, instead of plus 6.75 degrees Celsius, it would be plus 13.5 degrees Celsius. Plus 13.5 degrees Celsius. Right? So yeah, that's calorimetry. That's how we solve a calorimetry problem that involves a heat of neutralization. We have to figure out how many moles, multiply by the number of moles we have, multiply the kilojoules per mole times the number of moles we have, and then proceed with a normal heat capacity problem from there. We'll be doing some other practice problems like this in class today. Yeah, if you're confused, just a reminder that a lot of chemistry kind of comes in when you do learn by doing. So hopefully doing some practice problems together will help us out. Yeah, that's it for now, and I'll see you guys in class.